Welcome to this intermediate level webinar of the European Joint Programme for Rare Diseases related to Work Package 20 on key solutions to model longitudinal and natural history data with application to ataxia disease field. My name is Ralf-Dieter Hilgers. I'm the head of the Department of Medical Statistics at the RWTH Aachen University, and I will give this presentation. So within the webinar, I will touch about aspects on modeling continuous longitudinal data in the ataxia field, as the title says. And I will show you some transferability, because I think that the simple ideas which I applied here or which I introduced here will serve as a showcase for other potential problems as well. And that might be a good point to continue your research. So when having longitudinal data, e.g. from a registry, typical questions could be to model the disease progression and to inform about a randomized clinical trial, which I will come at the end of my presentation. So the topic which I introduce in my webinar comes to my consultation desk when talking about Friedreich ataxia patients together with Katrin Reetz from the Aachen group, and where we would like to model progression of these patients based on a large European registry about Friedreich ataxia patients. And the other side is my discussion with Andreas Traschitz from the Tübingen University, where we had some papers about the ataxia field patients, various types, and where we made some progression at that. And finally, the discussion with Katrin Reetz leads to a protocol of a randomized double-blind placebo-controlled parallel group design, and that comes to the point where you can see that these longitudinal data, may inform about planning a randomized clinical trial. So the outline of my talk is about the following. I will give some background and objective. I will give the description of the disease progression via modeling longitudinal natural history data. I will give application to the Friedreich ataxia field and to a very special type of ataxia in a very small population. Then I will give you some ideas about informing the design of a randomized clinical trials concerning sample size justification and borrow information of patients for use of randomized controlled trials. And I will end with some conclusions. So my main messages are, or the key learnings which I would like to bring to your mind, is that longitudinal natural history data are suitable for analyzing linear trends for disease progression, even in sparse data sets, that longitudinal data sets may have to be tailored, have to use a tailored modeling approach of the response if you have let's say, restricted value of the response variable. Then you can use a so-called Tobit model. We'll come to that in a couple of minutes. And then longitudinal natural history studies can, to a certain extent, inform about the planning of a confirmative comparative trial with respect to sample size justification, or giving some arguments about that, and borrow information from that. So let us start with the background and the objective. And what you typically have is a picture like that here, which are some sort of patients, 10 patients from the ataxia field, where you have typically very heterogeneous, let's say, courses of the patients follow. We have 10 patients Some only have cross-sectional data, which are the points, and some have some follow-up data over different periods and with different intensities. So talking about longitudinal data, that means I will consider only continuous measurements of the same primary endpoint variable at one or more unscheduled time points. These are available. And the primary interest is to model or to describe disease progression. And common challenges with these longitudinal data, and if you consider again the figure which we just have on the transparency before, could be that you have heterogeneous time courses, and that means the number of follow-up visits might be different. So you see it here, the whole ataxia patients are 519. We have 883 follow-up visits, and you can see that the number of visits, if you put that on a yearly basis, decreases dramatically. Only 6 of the patients have 8-year follow-up visits. That's the one point. And a second point, and you see it here immediately, that within the same time period, you have a different number of visits. That means that the visits are not really scheduled. And I come to the other points, missing observations and response with restricted range in a couple of minutes again. So let me give you some statistical terms which are coming on in the discussion more frequently. Heterogeneous time points can be described by left censoring, which means that you do not know about the patient disease history before entering the trial. The trial and with that the clinical databases. So you do not know, for example, from this patient what happens in the age of 20 or 10. The right censoring means you do not know what happens to this patient here above the 40-year age. The unscheduled visit, I already explained, is the number of visits within a particular time period differs, and is let's say not really planned before you see the patients. And the third one is the distributional assumptions of the scores. Often, which means that often the primary variable has a limited range of values, and this results in what is very well termed in the neurological context, sealed or flawed effects. And so probably we also might be interested in having different forms, like describing the data only by a linear regression model. You would like to have more informative functional forms, but I will not touch upon this in the talk because it goes beyond our scope. So the objective of the analysis, again, is to measure the progression and how the progression varies, for example, with explanatory factors. This is the sub-questions when I have solved the first question here. And there are typical statistical implementation which are used. And the one is to consider, let's say, the course of a patient at particular time points. And that must not be only one time point, it could be several time points. The second one is to measure the change, typically the change or difference from baseline. Even that one, let's say, as both approaches have their problems, and I will comment on the problems and give some warning messages, but I will more go into the third approach, which is progression modeling by linear trend, by using annual changes of the time course. So let's start the description of the progression model with the first approach, where you have a measurement at a single time point and how that can be derived from the data you have. So here we have first to overcome the left censoring of the data. So the left censoring of the data typically is solved by choosing a common zero time. So basically what is done is that the patients who enter the trial, that time will be set to 0. And the assumptions underlying that is that the cause is independent from the onset. So it is irrespective if the disease is considered for the patients who is entering in the database in the age of 12 years, or if he enters the database in the age of 40 years. So that might be a problem, and the correction for constant or strict linear progression needs to be done by covariables, let's say age of onset. So typically, this approach itself has some problems in it, but it can be corrected. In most situations, only taking a zero time is not a meaningful approach itself. A second one is a more major problem when talking about, let's say, measuring the disease progression at a particular time point, because that is related to the unscheduled visit. What is done here is that the time points are squeezed. You see here for this small time point with year 2, that we have this range of observations which are in it. And you see that if I take this time window here, I only have n equal 2 observations within the time window. So all other patients do not contribute to the comparison or to the description at that point. And that might be very frustrating, because you have a lot of more information from the patients. So that brings to the point that you increase the time window to to include more patients. Here we have included 3 patients data, but even that one is not really a solution. The point is that the time windows should be separated to each other. The point is that you assume that the response variable has a constant effect within the time frame you consider. And even that one might not be a good solution. Well, you can think about doing some mean value inclusion here, but even that one does not give a solution, because the green patient here does not come into play into this time interval here. And you would like to have a description of all patients at the point. Okay, so this squeeze of time points has some deficits in it. So let's talk about the description of the disease progression by progression of modeling the change, typically difference from baseline. So to sum up, this approach has a loss of information and could easily be improved. But I will come to that in a couple of minutes. So what is coming out? So to give you a visual, graphical visualization of that, I will show you first our original data here. I will need some, let's say, notation to make my description a little bit more formal. I call YIK the response or the score of a patient I at the time point K. And if I put K equal to 0, I have the response of the patient at the baseline value, time 0. So with that, I first do the time to 0 approach in my data because I need that. And then I will calculate for each patient and each time point the difference of the measurement at time k to the baseline value at time 0. So this is the difference from baseline to model progression. Some people and researchers think that might be a good idea to do, but it is a little bit a problem because you can have the same D difference or change if you have different baseline values on the one hand side. And so that might, with that, you might lose some information. So assuming that this is a valid approach, you assume that the baseline value is uninformative. Another problem occurs that if the range of the observation of yik, which is, let's say, in my example, a score, is different, is limited, but to a certain range. And if it is limited to a certain range, then people who start with higher baseline value cannot improve like what it can improve or decrease when they start with lower baseline value. So to show what happens in the figure, these are my original data here. I put some, let's say, connection with lines to my data. And here you see the difference to the baseline value, where you have set the 0 point. And interestingly, all start at the difference 0, but that's the way like you put it, and at a 0 time. And well, I must say, from my perspective, this looks a little bit, let's say, confusing if you have this figure here in mind, that this is the right description. And as you can see, the green one is the lowest curve here, whereas it is almost in the middle here. And it seems to be that the variation of the blue one is a little bit more impressive than the one here. Okay, some people think that it might be another solution to not put only the difference, then to put the relative difference from baseline to model the progression, which means that you divide the D from before, the difference between the case time points for the E's patients to his baseline value, and divide that by the baseline value. Well, that is some sort of another way to think and to, let's say, try to make data less variable than one has the data already at hand. But the problem is that with that relative expression here, you lose the linear model and you go to you lose the additive model and you go to a multiplicative scale model. This is only additive on a log scale. And what I mean with that is that only doubling the difference and the baseline value gives the same D. So you need to do something like that. And I think that is an approach which might be difficult to interpret and difficult to answer. So what is when baseline observations are not present, or when baseline observations are 0, then the expression is not valid? It reduces the variability within the patient with higher baseline scores, but increases the variability in patients with lower baseline scores. So to my extent, even that one is not a valid approach to model the data which you have. And so I would like to show you how the figures now look like, irrespective on the y-axis here, which is completely different. The difference scale gives you this figure. The relative difference scale gives you this figure here. And it appears to be that the variability at a particular time point, so between the patients or within the patients, is reduced. That might be good, but it is only by using this transformation of my primary endpoint value. So to sum up our consideration up to now, the approaches are not meaningful in most situations. Choose common zero time might be good, but only if you have, let's say, other explanatory variables. Squeeze of time points, I would not do this because you reduce the information, and both approaches are less informative. The difference to baseline to model progression is difficult to interpret if you have the relative difference, and the difference to baseline to model progression could be easily improved. So how should we do that? Well, I'm a fan of progression, the modeling of modeling the progression by a trend, and the simplest form is a linear trend on an annual change basis, and I will show you what I mean with that. So let's start with the figure again, where I connect all the data points, and I start with a zero time here, and the zero time is also here in this figure. And now I will not connect the data points. I just would like to show whether there is a linear trend in the data. So I compute the individual regression lines for each individual. And for example, the green one here is seen here because the last data point and the first data point is a little bit above the last data point, the middle data point is lower, and so the regression line is, let's say, negative. Well, of course, we only have 1, 2, 3, 4, 5, 6 regression lines because we have follow-up times only for 6 patients. And you might think, okay, the other patients do not contribute anything. Oh, if you do that in the correct way, the other patients with the cross-sectional information can contribute to the intercept of the model. So here you see for different patients, for my 10 patients, the intercept and the slopes of the regression lines. And what is basically done is that you can use a common approach, a joint approach, if you, let's say, mean all the regression lines to one regression line. To show what is happening now, if you don't use the zero time convention for the model, you can use the modeling linear trend and calendar time. So these are the patient data or original patient data. Here is the age of onset or age of entry into my database, and I can use the linear model here again. Here is our green patient with a slightly negative trend in that. Do not overinterpret the trend. Do not say, okay, there is a strict linear increase in the data, which might be, let's say, some sort of misleading if you, for example, consider the blue patient here at the end. But you see, overall, there might be an increase in the data for the blue patient, a decrease for the green patient, yeah, and so on. So when doing that, that means that you model the linear regression for each patient over the data point, and typically that could be described by a model like that. The assumption is that you think that the linear or monotone trend is, let's say, informative for you within the data, and it is acceptable to describe the data. But we have to figure out the distributional assumptions for that as well. Well, the extensions of the model are so-called linear mixed effects models with a random intercept and slope. I come to this in a couple of minutes. The second extension does consider the limited range of the response variables via the Tobit model approach. And the third one is to include, let's say, covariables, baseline, score values, and so on. So what do I mean with restricted scores, which I mentioned a couple of times? So let's go to this figure here. As I said before, sealed and flawed scores can occur. So that means, for example, if you have the SARA score could not go beyond the 40, and the SARA score could not go below the 0. So let's say here is an artificial example. Data could not be low or above a limit of detection. Here, a typical patient started with 0 SARA scores, then he has some certain increase, and then he rests at a 40 point SARA score. And when you do a linear regression over this data, you get that blue curve here. It's 2.8 plus 2.3 times the time value. And as you can see easily here, you might be dissatisfied with that. So what does that mean? Well, the observations on the top and on the floor here, they let's say bias our regression lines, and it would be good to, let's say, dissuade these observations, and that is done by the so-called Tobit model. It is, let's say, a truncated distribution which is fitted, and if I use this model, then the slope would be 4.8 instead of 2.3 times, and the regression model fits much better to what is go. Taking in the course of the data where the patient's SARA score increases. Here's the comparison. I think that the red one is, let's say, some better description than the blue one here, and I will give some recommendation to that in a couple of minutes. So this can be implemented easily in our linear mixed effects model, and that can be done. So the model is called the Tobit model because it originates from Tobin in 1952 in a completely different context. He proposes not to use for every case, let's say, the blue normal distribution for the residuals of the regression model. He said, okay, the data range is limited, so I take that into account and put the mass of the normal distribution in the active area here, and then the blue and the red one normal distribution occurs. So when should I do that? I mean, that seems to be a little bit complex. Well, there are some people discussing the pros and cons of that. For example, in 2009, one considered that, and they said that even if 80% of the participants reaching sealed observation at one occasion that could have some problems with the longitudinal data analysis model. Yes, that's right. And if the percentage of the patients, of the participants reaching seals at one occasion is larger than 20, or there are some important discrepancies between the parameter estimates from the two methods, which means the nonlinear mixed effects model and the topic models, then researchers should be cautious about the influence of sealed effects on the data. So this is also my experience. In my data set, I make these comparisons of the effects, and I would favor the approach of the 20%. So if 20% of the patients have sealed effect at one particular, let's say, time of the follow-up visit, then I saw differences between the topic model and the nonlinear mixed effects model. Well, on the other hand, it should be taken into account that fitting a topic model is a little bit more complex than just using the linear mixed effects models, and that is based on the numerical instability of the topic models, and in particular for sparse data. So that brings me to the point that I would not recommend the topic model in every case, but make the comparison. So I compare the parameter estimates of the linear mixed effects models and the topic models, and then I make a decision how to use it. So let's come to an example, application to Friedreich ataxia. Friedreich ataxia, we started with Katrin with a 2-year progression model. And interestingly, I mean, that's really interesting, is that the SARA score of all patients is rather linear over the 2-year expansion, and it is in between a certain range of the data. And you see here that we take into account also let's say, another covariable, which is the typical onset of Friedreich ataxia and the late onset. And you see that both curves differ, but have a linear increase. So then later on in 2021, we had the 4 years data. Here you see the data points. Here you see my total cohort. And you see even here, well, we have a rather stable number of patients over the 4-year period. And you see here the sealed effect patients, and the percentage is only 1%. So nowadays, I would like to say I'm allowed to ignore the sealed effect because they will not, let's say, affect my linear trend in the data. Even here, I made some different analysis for different covariables like ambulatory, non-ambulatory patients, and again, typical onset and later onset. So as I saw that no adjustment of the linear regression or the mixed linear effects model needs to be done because the number of sealed effects or fraud effect is below 20%. So this brings me to this figure. And I think that shows really brilliant that even in that case, the SARA score develops rather linear over the 4-year period. And interestingly, what we did in this scenario, we already would like to know whether the subscales, the 8 subscales of the SARA score, behave in a similar way. And what you see is that, for example, here, sitting has a much higher increase than all the other curves. And there was, let's say, some sort of decrease for the noise finger test. Okay, this was done in our evaluation data set. We used this data to plan a clinical trial, but I come to this in a couple of minutes. So you see, my linear mixed effects model provides a sufficient solution to the longitudinal data analysis of my registry. Of course, you may think, okay, these are very, let's say, complete data, and you are happy to have this. But I think the approach can also be applied to, let's say, sparse data set. And well, the check for sealed or flawed observations shows that we should not take into account it. Second example, where I would like also to let's say, give you some information about implementation and the journey, how to model the data, are my 18 patients from the Lewis-Barr syndrome, ATM cases, which I derived. So these are the 18 patients. Here is the calendar time, and here are the progression. And we would like to know whether there's a linear trend or not in the data set. So again, I used the zero time conversation. So put the time from baseline, and you already observed in the picture before that not all patients have data with follow-up. Some have only cross-sectional data. And the assumption here is that there is a comparability of the course of the baseline visits. And so now I'm starting working out. So the simple linear regression model, not taking into account the individual, let's say, course of the data and the linkage of the data to individual patients, is, let's say, is this red line. And you might be a little bit disappointed with this approach because, well, there seems to be a group of patients here, there seems to be a group of patients there, could be something like a covariable, and to have a decrease, which might be fostered only by these patients, might not mirror the data in a correct way. We statisticians say that the variance is not explained in the right way. So that is why we go to a model where we have a random intercept. So saying that the baseline, let's say, the baseline value of each patient differs or varies but randomly. And taking that in my model, resulting in a completely different solution of the fixed effects, meaning that the variance or the slope is now positive. It was negative before. And that could be one solution in my data. And here you see typically what you have to say. You take a random intercept and you link the data which are coming from each patient. All other aspects, which is more or less the code of SAS software, which might not be available for everybody of you, but you can do similar things with R or Python or some other good programs. So then I put also another variable as a random variable, meaning that the slope varies by random for each patient. And you see that my solution of the fixed effects are not affected here. And well, that could be done, but for the sake of simplicity of my model, I would not increase my model with that one here. What I would like to show you on my next transparency is how look the data if I go back to my original approach, having the calendar time here. If you take the calendar time here and you put the regression model on the data here, And now my model has something like, which I call follow-up time, which is a calendar time here. And I account for different baseline SARA scores here in my observation. And I say that the progression is related to the baseline SARA score, which I measured. But you see here, this p-value is below 0.05. So the slope of the patients does not change individually. I could forget that. And I can come up to, let's say, the other parameters. Even here, you see no one of the variables is explanatory for my sparse data set. And I don't, I will not wonder about that because the data are really sparse, and to see clear trends, even with my sophisticated model, might not happen. So what I would like to point out is that a lot of things have to do when fitting models like that here. And that means you should consider the residual plot. So probably there are some assumptions, the normal assumptions, which might not be fulfilled at that point. Then there might be some observations at particular time points which have a great impact on the estimates. So even that one should be detected by an influence diagnostic. And you should consider, let's say, some sort of measurements of model fit improvement with that. And well, in linear mixed effects models, you also have to consider the appropriate covariance structure in the data. But these are technical terms, and I will not go into depth with that because we would have a clear, we would just have to have an impression what we can model with our data. And so I'm almost coming to my last point, inform about the design of a randomized clinical trial. So that means my longitudinal data analysis give me some information, let's say the progression, the linear trend, and probably you can formulate your primary endpoint with that. But what is the difference between a randomized clinical trials and a nonlinear longitudinal data from a registry? But there are lots. And from the data point of view, I think that in randomized clinical trials, there's typically a completely different situation. You have scheduled visits, which are planned before. And this causes, if some patient does not come to the visit, which is planned in before, missing values. Well, we can handle that in two ways, by linear mixed effects models or multiple imputation techniques, or using these MMRM models, which are mixed model for repeated measures. Second, similarity. By strict inclusion and exclusion criteria, you think, well, I have a very homogeneous group of patients, which allows me to compare two different treatments. Well, that can be increased by stratification. And probably the covariables used for stratification or some other covariables can be used in a sensitivity analysis. A sensitivity analysis has a different meaning in longitudinal natural history course data analysis. Then the repeated observations causes repeated observations based on the scheduled visit causes multiple testing, because here you would like to to compare at particular time points. But even here, I think you run in the same problem with these time points as you have that in the natural history data described before, and I would favor a linear trend model. And third, multi-components of the, let's say, multiple endpoint or of the composite endpoints might be interested to analyze. So here the individual scales are of interest, and item response model or linear mixed effects models can be used. So, missing data, you would not have missing data in such an extent in our registry data because you have not pre-planned time with it. So let me come to two aspects which I would like to show you a solution in my data. The first aspect is sample size justification on the one hand side. So how can the sample size justification based on my, let's say, linear progression model for the SARA score be informed for the comparative clinical trial? So that is the one aspect, and the other aspects I come in a minute, which is borrow information. So let's talk about the sample size justification. So I used my Friedrich Ataxia patient data, used the covariance structure, which I have in my data. I found a slope of 0.82 increase per year for the patients. We assumed that we would like to have a new treatment reducing the slope by 50%, and we would like to plan a two-arm parallel group design for that. And what we found out is in our situation, well, I here put three lines. The first line is for a trial which lasts 12 months. The blue one is for a trial which lasts 24 months, so 2 years. And the green one is for a 3-year trial. So then I put 3 visits on the 12 months trial, and you see that you have about 450 patients as a total sample size. And if you prolong the duration of the trial to 2 years, then we are in another situation because you are, let's say, in with 4 visits, visits every 4 months. Here in the 2-year trials, in a situation of 270 patients, which is, let's say, some sort of half the number of patients. A further increase I would not reach in my situation, which is basically related to the variance in the estimates, which I have in mind, and you should carefully figure out. So what I mean is you have a certain gain in doing a longer trial, a smaller gain in, let's say, increasing the number of visits within that trial. But I come back to the assumption which I made because I included a random slope and a random intercept in my sample size justification. And here I see, here you see how sensitive my approach is if I take different values of the random slope and the rest variance in my data. The first row are the data from my original approach with the 12 months trial with 4 visits. So then I said, okay, 0.993 is almost 1, and the 2 point is 2, and you see this rounding does not have any real real effect on my total sample size. But if the residual variance is underestimated and is doubled, then you see that the number of total sample sizes increases much. And if the variance estimates is overestimated and it is only half of what is initially assumed, then you see that the total sample size is increasing. So I would recommend nowadays to do these, let's say, sensitivity analysis for the sample size calculation, because you never know whether you can see the 0.993 and 2.0981, which must not be taken seriously. You see the rounding has no big effect, but whether you see these variances or also in your randomized trial. The second point, which I would like to briefly discuss, is the topic of using the data from the registry in my, let's say, clinical trial by borrow information of that. So what is the legitimation for that? And I'm using only partly this information. I know there is a lot of discussion right now to do a single arm trial and then put the data from the registry as a control arm. I will not go in that way. I will only use the sum of the historical control data from the registry and feed in the randomized trial. And probably I can, let's say, end with a smaller randomized trial in that situation, because I already have that information at hand. So this approach is, let's say, stimulated by the FDA guideline on rare diseases natural history data, where they set a hybrid approach using external control data to add to a concurrent randomized control arm in a randomized control might be useful. Other situations which follow similar approaches or different approaches statistically are Bayesian methods, meta-analytic methods, and frequentist methods by Phiele in 2014. And I will follow the frequentist approach. I have to mention that POCOG has, let's say, a sort of 6 criteria which must be fulfilled that the control arm data from the registry could be considered as, let's say, comparable to the control data in the randomized trial. And that should be taken into account, which takes, let's say, the standard treatments should be the same and precisely defined. The controls, he favors that the historical control data must be apart from a clinical trial. The method of treatment evaluation must be the same, measurement of the primary endpoint, patient characteristics, and so on and so on. But what's coming up? So our approach is the so-called fill-it-up design, which was introduced by my co-worker, Steffi Wietz, in 2024. And hope that we can publish the paper soon so that you can read what's going on. So we think that we start with a smaller randomized clinical trial, and then at a particular time point, we make an equivalence test between the control patients of the randomized trial and a set of historical control data, which are coming from a registry and considered to be, let's say, potentially similar to the control patients in the randomized trial in terms of inclusion criteria and so on and so on. And that must be done before. And if we show equivalent, then we end up with a trial which has NE dash and NC dash plus NH patients. If we cannot show the equivalence, then we have to do further recruitment until we end with a number of patients which were pre-planned NE and NC patients. So the equivalence trial is a pre-test, and so we have a multiple testing problem here, and we solved that problem. And there are certain, let's say, certain questions which are coming from that trial. So the justification for this design is that further recruitment is very difficult, and if I have a certain amount of patients in my trial, it would be good to use them, and so to let's say to end with a smaller trial in that perspective. So what has to be taken into account? So the hybrid approach is in line with the FDA guideline, and that's good. We implemented the multiple testing, a strict multiple testing problem, which preserves the type 1 error probability. The problem is that the last test is not a superiority test, it's a non-inferiority hypothesis. You might think that is a disadvantage, but well, if you use such an approach, there must be something you have to pay for it. What our simulation shows is that at least 50% of the initial total sample size must be used in step 1. So this is under particular situation, the situation which are coming out. There might be some power gain, and we would like to recommend that approach only where a few patients can be enrolled, and the procedure can have some power gain if good and suitable controls can be identified before. So I show you what happens with the power gain. So taking an effect size of for a continuous variable of 0.5 and having, let's say, 500 historical control data, then you here see the 138 patients is a total sample size of, let's say, a 2-arm parallel group design with fixed sample size. So our approach, our fill-it-up design, stops with 74 patients to do the equivalence test. And then you end up with 74 plus 500 if the equivalence test allows you to pool the control data with 74 plus 500 patients in the trial, which is much more than the 183. If you don't do it, then the average sample size has to go to, let's say, the 183. And because of the probability, most statisticians think about the average sample size, which is 136, which means that it is much likely to go directly into the ended final sample size. The power is 90% in both cases, so that's the story. And you can derive similar tables for different sets. The number of controls cannot be increased over a certain amount to having an effect on the characteristic of the design. So if you have, let's say, 1,000 patients or 1,500, that does not make any difference anymore. My conclusion is, from the lecture, do not squeeze the data by the time points. Use linear regression models to model the time trend in your data. Use the linear mixed effects models, allow for formulation of the progression model. I like that very much. Probably consider the Tobit models. And then you can derive some information to plan a clinical trial with respect to sample size justification or with respect to borrowed information. So with that, I would like to end up my webinar at that point, and I'm happy to answer questions. You find me on the web and the EGPRD website, and I wish you very much pleasure with your research on rare disease trials. Bye-bye. Thank you for your attention.